I'm Buddhima Weerasinghe from Sri Lanka, actually. So I'm from University of Colombo School of Computing, Sri Lanka. And my co-authors are Asanka, Sayakkara, Kasun, Zoysa, and Scanlon. So I have quite a different story, actually. So I just finished my undergraduate degree and will be starting my PhD in September. So I'm quite in the transitional period, and this paper is based on the final year research that I did in my undergraduate research. So the title of the paper is Low Overhead Non-Invasive Electromagnetic Side Channel Monitoring for Forensically Ready Industrial Control Systems. Give me a second. So before we talk about this particular paper, okay, give me a second. Let's talk about my final year research. So it was titled Malicious Network Activity Detection Through Electromagnetic Radiation in Wired Ethernet. So we have so many concepts here. So let me discuss few of them before we go into the content. First one is electromagnetic side channel analysis. So what is EMSCS? So it is the domain where we study unintentional radiation emitted by computing devices. So it could be an Ethernet cable, a laptop, mobile phone, whatever it is. And the nice thing about this technique is that it's non-intrusive. So we are not getting into the network or the device at all. We are not harming it. And this brings early threat detection because we are at the physical layer. And then this could add value to existing security measures. And most importantly, this is resilience to encryption because we are not looking at the real data itself, but the radiation that it generates. So the aims and the objectives. So this was a proof of concept research. So what we aimed to explore the potential of electromagnetic side channel analysis in malicious network activity detection in wired Ethernet. So, and we have few other objectives like investigating the network traffic's relationship with the electromagnetic radiation patterns, identifying a method or an algorithm that we can use to detect and classify malicious network activities and evaluate that method's effectiveness, and finally to explore the practical applications of this mechanism on which this paper is written. So when I talk about the related works to this particular research, it could be divided into two groups. First one is exploiting EM radiations of Ethernet cables. So there are researchers where they have exploited radiation of cables mainly for the attacking purposes. So to create covert channels, papers like Lantana, Trust the Wire, such papers. And there's another part where they have used electromagnetic side channel analysis for malicious activity detection in computing devices like mobile phones and IoT devices. So papers like Evidence are for that. So I bring these two concepts together where we use the radiation of Ethernet cables in attack detection when a traffic is passing through it. And then this is the title of the paper. So an application of that particular research. So again, it has so many concepts. Let's first study what industrial control systems are. So industrial control systems are any specialized computing devices that manages critical infrastructure like power grids, wastewater management systems, transportation, natural gas, as well as process automation systems like nuclear power plants, oil refineries, and steel mills. And most of these networks are wired. And then we are going to forensic readiness of these systems. So we know there have been so many attacks to these systems. And in the worst case, they could harm human lives as well. So as much as it is needed to stop such attacks, it's very important for us to be able to investigate when such attack is happening. So designing an ICS or an industrial control system to proactively support efficient, effective digital forensic investigation is called making it forensically ready. So making it forensically ready, we can prevent production downtimes during investigations, and we can provide rapid incident responses, and we can analyze the root cause quickly, and we can be compliant with the regulations, and we can support legal authorities with good evidence. So one thing that we can do in making our system forensically ready is like continuously logging the critical system events like network traffics, PLC commands. But the challenge that we have with this is these legacy devices that we have in industrial control systems don't have much logging capability. They have very less storage, and continuously monitoring traffic patterns, recording them is computationally very expensive. So we need a methodology that doesn't add overhead and make the network more complex. So that's where this electromagnetic side channel monitoring comes into the talk. So now let's go to the research methodology. So we know network cables emit unintended radiation when traffic passes through it. And we have the hypothesis that this EM radiation reflects the malicious network traffic. So the approach is we need to capture the signals first, and then we have to analyze it to detect network attacks. So when it comes to our experimental setup, it's of two parts, software setup and the hardware setup. And in the software setup, we had a setup for data collection and another part for data analysis. So this is a simple drawing of the hardware setup. So we created a very simple point-to-point network. This is a proof of concept research actually. So we had a PC as the attacker, a desktop computer, and a broadband router as a victim, and a Cat6 cable connecting those two. And we send an attack through this cable and capture the radiation using a HackRF1 SDR device with a H-loop antenna in touch with the cable. So for the ease of automation, we use the same attacking device to record the traces as well. Of course, you can use another device as well. So software-defined radio is a simple device that has most of the radio functionalities in the software form, like modulation, demodulation, amplification, and so on. So software-defined radios are using complex in-phase quadrature phase sampling. So at each point when a sample is taken, it's of two values, in phase and the quadrature phase. So it's a complex value. So when we say EM trace, it's just an array of complex numbers. So here the sampling rate is equal to the captured data's bandwidth, and we have used 20 megahertz sampling rate. That's 20 million samples per second. So if you collect data for 30 seconds, you will end up with 4.47 gigabytes of data. So now we come with another problem, like we don't have a data set. So there are no any publicly available electromagnetic traces data sets. So we had to create one ourselves. So rather than us creating attacks, we wanted a realistic attack data set. So therefore, we found this CIC IoT 2023 data set. This is by Canadian Institute of Cybersecurity. They had 33 reproducible traffic patterns in their data set, so in the form of PCAP files. So we took these PCAP files, replayed them, and simulated the attacks. So meet the scope, we only chose 3 out of them, though it has 33 attacks. First part in the data collection was to find the emitting frequency. So same as we have a frequency for FM radio channel. So if you want to listen to something, we have to tune for that. Same way, all the cables or the devices, they have a frequency where the data of that device get leaks to the outside. So first we need to find it. For that, we had a simple software setup, and we started from 30 megahertz and went up until 260 megahertz to find that frequency, and we simulated one attack, namely DOS HTTP flood, and together with the benign traffic. So benign traffic is when we have not playing any attack. The network is at its normal state communicating. And once we collected that traces, so this is the data set. So we collected traces for like 3 hours, and the size of the data set is around 100 gigabytes. And finally, we used a dissimilarity analysis algorithm to find a frequency at which these two trace patterns are mostly dissimilar. So we used normalized cross correlation and cross correlation. And then this is the plot once we analyzed using that algorithm, and we can see at 240 megahertz, the traffic patterns are very dissimilar. So you can see the benign traffic going in green color at the bottom, and then the attack traffic going at the top. So it's very distinguishable. So now we have the emitting frequency identified. We should collect traces for attack detection. So here we collected traces at 240 megahertz, and we simulated all three attacks, namely DOS HTTP, DOS UTP, and DOS TCP, together with the benign traffic. And then that data set is of size ITZV. And then we collected data for around 2 hours. And then we plotted the traces against each other, and we can see the different trace patterns. Like we can see the normal traffic going at the very bottom and HTTP flood again on the top, and then the other two also. We can see that its HTTP flood is little more distinguishable than the other two, quite different. So us being able to see it like this is not enough. We need numbers. We need to automate this process. For that, we used machine learning, very lightweight 3 machine learning algorithms, namely random forest classifier with ADA boosting, multi-layer perceptron and supportive vector machines, and we calculated accuracy, precision, and recall, and we evaluated using top 1 testing accuracy. So this is when we train the machine learning algorithm. So these are the accuracies that we got. So DOS HTTP flood is most recognizable. And then we have TCP flood in the second place and UDP in the third place. And we can see random forest classifier with ADA boosting performs better than the other two. And then we have few scenarios. First one is to verify the probe location. So what is the optimal probe placement when we are capturing radiation? So we can keep it in touch with the cable, take it 1 centimeter away or 10 centimeters away. So what is the optimal placement? So this is when we keep the cable in touch, keep the antenna in touch with the cable. So the same thing we got earlier. And this is when we get the antenna 1 centimeter away from the cable. So you can see like we can't see anything separately in this one. And this is when we take it 10 centimeters away. So it's the same thing. And then we train the models and you can see like the accuracy drops drastically when we take the antenna at least 1 centimeter away from the cable for all 3 attack types. And then the next one is when splitting into thirds. That's like to find out which phase of the attack is most detectable. Is it the beginning? Is it the middle or at the end? So what we did here was we collected the trace throughout entire period of the attack, and then we split it into third parts as the start, mid, and the end, and then we train the machine learning models. So these are the results that we got. So we can see at the middle the attack is more detectable, of course, and then at the beginning as well as at the end accuracy is little less, but still for the most of the attacks we can detect it as well. It has a good level of accuracy. And next part is reducing the sampling rate or adjusting the sampling rate. As I mentioned, we are using 20 megahertz sampling rate. So it's very high in dimension, the amount of data. So if you are using this in a very resource constrained device, running the ML model and making the analysis is quite difficult with this much amount of data. So we try to reduce the sampling rate to see whether reducing the sampling rate would affect the detecting accuracy. So here we only used this for HTTP flood because other two already had very less accuracy. So we can see for the random forest classifier and the support vector machine, the accuracy is not dropping. Even though we reduce the sampling rate for from 20 megahertz to 10 and then to 4. And if you are using multi-layer perceptron, accuracy drops when we reduce the sampling rate. So last one is to see how the environmental effects affect our detection accuracy. So we have 3 setups. First one is the setup that we discussed earlier. Second one is we took the entire hardware setup to a different place in our lab, and then we replayed the same pickup files, collected the traces, and trained the machine learning algorithms. And the third one is in that place, we changed this victim device into another device, and then collected the traces in that situation as well. So this is what we got in the first place. This is the second setup. So you can see the radiation is much different in that environment. And this is the third one. So it's again lot different. So we can say like, yes, environment do affect the detection accuracy, and these are the results. So you can see, even though in the first setup, the UDP and TCP accuracies were less, it is increasing in other setups. So the key experimental findings of this research is probe placement do matter. And then detection accuracy varies for different attacks, and the observation time affects the detection. And sampling rate do affects once we reduce the sampling rate. So for some models, the accuracy drops, and the environmental factors would affect the accuracy. So now we are going back to our title, how we use this in an industrial control system. So we are suggesting monitoring nodes which have the capability of capturing the EM radiation, running an algorithm and making the prediction. So if it feels something anomalous, it could trigger a packet sniffer who could collect traces when if something anomalous is happening. So we can place them in these different places of industrial control system. So it is of 3 levels, 4 levels actually. First level is industrial workstations, and then we have the human to machine interface and PLCs, IEDs, and RTUs, and then finally where the actual work happens in sensors and actuators. So we can place them strategically in places we think it's needed, and then we can do it. So monitor nodes placed at strategic points in the ICS infrastructure. And these nodes detect network threats using EM radiation, and then they can alert trigger forensic mechanisms on demand, like activating packet sniffers. And the advantage of this particular approach is this does not add extra load to the ICS network, and they operate independently on the monitored system. So we don't have to shut down the system to collect traces. And when we go to the future work, we have a lot to do. This was just a proof of concept research. We proved that yes, we can use radiation in attack detection, but then we have a lot to do more. So we have to enhance these ML models. We use very simple ones. And then we need to test this in mixed traffic environments. And if there are any alternative approaches, we have to find whether there are any more. So like using cross correlation or wedge PSD calculation algorithm. And if in our environment the accuracy of other 2 floods or whatever the flood is less, we should try to improve that accuracy as well. And we have to develop this dedicated monitoring nodes as a future work. And then we have to expand the threat model to detect additional ICS cyber threats. So we only tested this for 3 attacks. Even the dataset that I used, it has 30 more attacks. So we should expand it to do that. So yes, that's it for my presentation. Thank you so much.